If you've been on YouTube over the last few years, you've probably seen videos like AI learns to walk, or destroying Donkey Kong with AI. These videos are incredibly cool. They showcase some of the most exciting work in artificial intelligence. But if you're anything like me, you've probably walked away a little bit unsatisfied. A lot of the explanations are extremely high level. Something like, we reward the agent for doing good things, and we punish it for doing bad things. And while that's technically true, it doesn't really explain how the learning actually happens. So in this video, I want to break down reinforcement learning in a way that's intuitive and concrete. We'll walk through everything step by step using a Mario agent as our running example. And if you want to follow along, all of the code I used will be linked in the description alongside a tutorial on how to build this exact setup on your own computer. So let's get into it. So how do we go about defining a reinforcement learning problem? And what does it take to solve it? Let's take Mario as our example. In a 2D Mario game, the goal is pretty simple. Get from the start of the level to the end of the level. To do that though, Mario needs to move to the right, avoid enemies, jump over gaps, and navigate any other obstacles along the way. So the task itself is easy to understand. But how do we actually go about teaching an AI to do this? In reinforcement learning, our goal is to train an agent to learn something called a policy. This is usually denoted by pi. A policy is simply a rule that tells the agent what to do in any given situation. More formally, it's a mapping from states to actions. So what does this actually mean for Mario? A state is what the agent currently sees. In our context, these are the images of the game screen, the same thing a player would see. And we can get this from the game's memory. An action is what the agent decides to do. It could be move right, jump, or do nothing. These are the same buttons a player might press. So at every moment in time, that means each frame of the game, the agent observes the current state, the screen, and the policy tells it what action to take. But not all policies are created equal. Some policies will make Mario run into enemies immediately. Others might get him all the way to the end of the level. A policy can be good or bad based on how well it actually performs at the desired task. Our goal in RL is to learn the optimal policy. This is often denoted as pi star. The optimal policy maximizes something called the expected return. Now that sounds a bit complicated, but it just means we want the agent to choose the actions that lead to the highest total reward over time. In other words, we want Mario to play the game as well as possible, not just in the next step, but over the course of the entire level. So we said our goal is to learn a policy, a rule for what Mario should do. But here's the problem. How does the agent know which action is good? That's where the Q function comes in. In Q learning, we learn a function called QSA. You can think of it as, if I take action A in state S, how good will things turn out? More specifically, it answers, how much total reward can I expect in the future if I do this? Let's go back to Mario. The state is what Mario sees, the game screen, and the actions are things like move right, move left, jump, jump right, and so on. The Q function takes in the current screen, one possible action, and it outputs a number, a Q value. This number tells us how good that action is. Imagine Mario is standing next to a pit. If he moves right without jumping, he dies. So QS right might be something like -1. If he jumps over the pit, he survives and keeps going. So QS jump right might be something like +5. The Q function is basically just scoring each possible action. Now here's the key idea of Q learning. If we know the Q values for all actions, we can just always pick the best one. That gives us our policy. Always choose the action with the highest Q value. So instead of directly learning a policy, we learn Q, and the policy naturally comes from it. This is why this method is known as an off-policy method of reinforcement learning. You may be asking, what do these Q values actually represent? Well, we can't learn arbitrary reward values. We need them to embody the expected total future reward. That means we aren't predicting just the immediate reward, but everything Mario will get after that action. Let's look at a simple example. Imagine a small grid where Mario needs to move to the right to reach the goal. Each time he moves closer, he gets a one-time reward of +1. From the starting position, there are 4 steps to the goal, so the total future reward equals 4. Mario takes 1 step closer, the total future reward equals 3. Then 2, then 1. So the Q value should reflect how much reward is left in the future. Actions that lead toward the goal output high Q values, actions that lead towards death output low Q values. So if Q is accurate, the agent naturally behaves well. There's one more important detail we need to discuss. The discount factor, denoted by gamma. Gamma controls how much we care about the future. Why do we need it? Because without it, the agent might waste time. Suppose these 2 action sequences both reach the goal. The first, go straight to the goal, right 4 times. Or the second, waste some time right left, and then go to the goal. Since each reward can only be gained once, without discounting, they both give the same total reward of 4. But we want the agent to be efficient, so we apply a discount. Rewards further in the future are worth slightly less. Let's apply a gamma of 0.99 and see what happens. Before gamma, what we have is the basic return. The return is just the total reward we expect starting from the current moment. Without discounting, that's simply the current reward plus the next reward, the one after that, and so on. The problem is this treats all rewards equally. That can make the agent inefficient as we saw before. So we introduce gamma, the discount factor. Gamma leaves the immediate reward unchanged, but gradually reduces how much future rewards are worth. With gamma set to 0.99, the next reward is worth 99% of its original value. The reward after that is worth 99% of that value, then 99% again. So distant rewards matter less and less over time. This encourages Mario to prefer faster solutions instead of wasting time before reaching the goal. So let's go back to our example with the slow and fast path. With the fast path, we receive a total reward of 3.94. But with the slow path, rewards come later, so they get discounted more. Its total reward will only be 3.88. So faster solutions get higher Q values. To summarize this whole section, the Q function tells us how good an action is. It measures the expected future reward. By picking the highest Q value, we get a policy. So at this point, we've defined the Q function pretty well. But now we hit a big problem. We don't actually know this function. So how do we learn it? One of the most powerful tools we have for learning unknown functions is something called a neural network. At a high level, you could think of a neural network as a flexible function that we can change shape to match data. In fact, neural networks are often called universal function approximators. This basically means if you give them enough capacity and the right training data, they can approximate almost any function. Let's take a look at a simple example. Suppose we want to learn this function, y equals x cubed. But imagine we don't know the formula and we can't see the true function line like we can here. All we have are some noisy data points that kind of roughly correspond to the way this function looks. Now we start with a random neural network, basically just a random curve. We compare its predictions to the real data, then we measure how wrong it is and adjust it to reduce that error. Over time, you can see the network slowly bends itself to match the true function. The most important takeaway is, if we have examples of correct behavior and we have a way to measure its error, we can train a neural network to approximate any function we care about. Now let's bring this back to RL. Our goal is to learn QSA, which is just another function. So in theory, we can use a neural network to approximate Q. In the x cubed example, we had clear labeled data. The input mapped to the correct output. But in RL, we don't actually know the true Q values. So how do we train? Instead, we use something clever. We use our own predictions to create targets. This idea is called bootstrapping. Let's take a look at this example. On the left, we're in state S, and we choose to go right. This gives us a Q value of 2.97. That action takes us to the next state, S prime. Now in this new state, the best action is again go right, and its value is 1.99. Let's take a look at the equation on the left for a moment. Recall that 0.99 is coming from our gamma factor we discussed earlier. So this value right here is the reward we immediately get for choosing right. Everything else is just the future reward, the rewards we expect to collect later if we keep making good decisions. If we pull out a factor of gamma from the future part, we get this equation. Now look closely at the part inside the parentheses. That's the same expected future reward from the next state we see on the right. In our simple example, the best action in that next state is again move right, so this is just QS prime right. More generally though, we don't assume the next action is right, we assume the agent chooses the best possible action, and that's just denoted by this, with the max with respect to A prime. This gives us a really important relationship that says the current value equals the immediate reward plus the discounted future value. Now, if our Q estimates were perfect, both sides would match exactly. So if we rearrange our equation, we get that it equals 0. And plugging in our example values, we see that this holds true. 2.97 minus 1 plus 0.99 times 1.99 does in fact equal 0. Perfect. But in reality, we don't know the true Q values. Instead, our neural network gives us estimates. Maybe it predicts QS right equals 3.55 and QS prime right equals 1.82. Now if we plug in these new values, we get a result of 0.7482, not 0. This means our initial estimate was wrong. And that difference is exactly the training signal we use to improve the neural network. Measuring how far apart this new value is from 0 gives us our error. This difference is called the temporal difference, or TD error. It's called temporal difference because we compare our prediction at the current moment to a target built using information from the next moment in time. The TD error itself is this equation we saw earlier. If this value is 0, our estimate was perfect. If it's large, our estimate was poor. When training the neural network, we square this error. Squaring does two useful things. It makes all error positive, so negative and positive mistakes don't cancel out, and it punishes large mistakes more heavily than small ones. During training, we repeat this process constantly. At each step, we record the current state, the action we took, the reward we received, and the next state, and then whether or not the episode ended. Using this information, we build a TD target, measure the error, and update the neural network to reduce it. That's how Mario slowly learns which actions lead to success. This method altogether is known as a deep Q network, or DQN. So what does all of this actually look like in practice? Let's show off how our Mario agent learns throughout training. Everything you're about to see is just this one idea applied over and over again. As you saw from that gameplay, deep Q learning can be a powerful tool for reinforcement learning. I want to quickly run through a few practical implementation tricks that actually make DQN work in practice. All of these I use to get the result you just saw. The first is frame stacking. If we only give the agent a single image, it has no sense of motion. Mario could be moving or enemies could be moving, and we really couldn't tell from just a single image. So instead, we stack several recent frames together. This gives the network a short memory and lets it infer movement. The next is RGB to grayscale. NES frames are full color images, but most of that color information isn't really important for gameplay. So we convert the images to grayscale, and we shrink it. This dramatically reduces the input size, making training faster, while keeping the important structure intact. Next, there's frame skipping. Instead of choosing a brand new action every single frame, we repeat the same action for several frames in a row. This speeds up training massively and makes actions feel more meaningful. Jumping over a pipe actually means Mario has to hold the jump button for many frames in a row. To get over some obstacles, Mario might need to hold the jump button for 12 frames or more. With a frame skip of 4, Mario only needs to select the jump button 3 times in a row as opposed to 12, which is much more likely early in training. Next is random action selection. Early in training, our network knows basically nothing. If Mario always followed the best current guess, he might get stuck repeating terrible actions forever. So sometimes we force random moves, just to explore the environment and discover better strategies. Now for one of the most important tricks, the replay buffer. Every gameplay step gets saved into memory. But instead of training on only the newest experience, we randomly sample old experiences from this buffer. Think of it as training from old video data. This breaks up correlations in the training data and makes learning much more stable. Finally, I want to discuss the online network and the target network. The online network is the one we actively train every step. But if we also use this constantly changing network to generate our training targets, the goalpost keeps moving. That makes learning very unstable. So we create a second network called the target network. Now this is just a frozen copy of the online network that only occasionally updates. This gives us a more stable target to learn from and has the following equation for our TD error. Without tricks like these, DQN tends to completely fall apart, so it's important to implement all of them correctly if you want a successful agent. And that concludes my explanation of the DQN algorithm. If you made it all the way to the end, thank you. Reinforcement learning can feel pretty intimidating at first, so I hope this video made the core ideas a little more approachable and help you build your intuition for how these agents actually learn. I'd love to keep making more reinforcement learning and AI-related videos in the future. So if you have any questions, topics you'd like to see explored, or ideas for the future, let me know in the comments. Thanks for watching, and I'll see you in the next one.